Let's talk about playing cards, which are a popular way to explore ideas in probability. So I'm going to be talking about a standard American playing card deck. In such a deck, there are usually 52 cards, and each card has two important properties. One is its rank, which is an arbitrary value. In this case, we have A, 2, 3, 4, up through King. For those of you familiar with these cards, often A is actually the highest rank, but we don't care about the ordering. So there's just 13 distinct ranks. And then there are also 4 what are called suits. And these suits are these 4 particular shapes that are so popular, they're part of Unicode. We have the spade, the heart, the diamond, the club. And then here are all of the different cards. There's 52 cards, which are just all the combinations of ranks and suits. Okay. So first let's talk about what happens if you take such a deck of 52 cards and you shuffle them. So they'll go into some arbitrary order. And the question we might ask ourselves is, well, how many different orders are there? Well, there's 52 factorial. We know that the number of permutations of n things is n factorial. So that's roughly 8 times 10 to the 67. And what that means is your chance of getting any particular permutation is going to be 1 in 52 factorial. So I think when I first learned this, I was a little surprised that when you shuffle a deck of cards, you get an ordering of cards that has never been gotten before. With extremely high probability, it's unique. Okay? Like I would bet basically anything that no two actually mathematically sound shuffles where you're really truly mixing everything up have ever been the same. Just basically never happened. Okay. So let's think about some interesting experiments we can do with these playing cards. One is this game called poker. And I'm not going to go into all the rules, but it's very popular. People gamble. There's whole TV shows about it, all that. And in the game of poker, the classic version of the game, you're given 5 cards. And those 5 cards are from this set of 52. So this set of 5 cards is known as a hand. And an example hand would be you got the ace of hearts, the 2 of clubs, the 5 of clubs, the king of clubs, and the queen of diamonds. And then there's ways to rank the different hands, and you want to have the most high ranking hand. And I won't talk about any of those rules today. But point being, you draw 5 cards from this deck. So question for you. If we think of each hand as a random experiment, what is N? So what's the cardinality of the set we're drawing from? What is K? What is the size of our sample space? Is the drawing happening with or without replacement? And is the probability space uniform of collecting hands? So think about this. Again, I encourage you to try and do it on your own and then check your answers with what I'm about to say. So my answers are, first, the cardinality of the set we're drawing from is 52. There's 52 different cards, and K is 5, and we're drawing without replacement. So that's where it fits into our framework from before. Okay. What's the size of the sample space? Well, we'll leverage this information that there's 52 draws, or there's 52 items in our set. We're drawing without replacement, 5 of them. This is just going back to our counting lectures. So drawing 5 items without replacement from a set of cardinality 52 is 52 choose 5. That is, there are 2,598,960 possible hands. Okay? And lastly, is the probability space uniform? Yes. Doesn't matter. Each draw is independent, so the space is uniform whenever we draw a poker hand. Second question for you. Which of these hands do you think is more likely? Okay, we have one hand where we got a 2 of hearts, a 7 of spades, 8 of clubs, queen of spades, 8 of hearts, ace of hearts rather. And then we have the other one where it's all of the highest ranking poker cards, all the heart rank. Which one's more likely? So if you got that, you would be very happy. Effectively unbeatable. By the rules of poker, which I haven't told you yet. Or I won't. So which hand's more likely? Turns out neither of them is more likely. They're equally likely because we said it's a uniform probability space. So if you said it's a uniform probability space, but then you felt like the royal flush was less likely, you hadn't really truly digested what uniform probability space means in this context. That's what it means. It means all the hands are equally likely. Okay. One more thing we're going to do with cards here. Let's talk about the probability of getting what's called a flush. So this is a certain type of hand in the game of poker. It means all of the 5 cards that you have the same suit So they're all hearts, they're all clubs, they're all diamonds, they're all spades. Any of those 4 possibilities. So what's the chance that your hand is a flush? And again, I encourage you to try and work it out. If you get stuck, I'll reveal it and then pause as you get unstuck. Okay. So first I'm going to note, because it is a uniform probability space, all we need to do is count. Just back to the counting lecture. So we need to count the number of different flushes. Okay. So one of them is here. How do we do that? Well, we're just going to build on what we did earlier in today's lecture. So first I'll note, how many different heart flushes are there? How many different ways are there of getting 5 hearts? Well, there's 13 hearts in the deck. So if we want to think about the process of enumerating all of the different possible combinations of hearts, then we're going to be choosing 5 out of that set of 13 possible ones. So there's going to be 13 choose 5, which is 1,287 heart flushes. We're not done, because we also need to think about all the different suits. So there's 4 different suits. The total number of flushes will be 4 times that. So there's 1,287 heart flushes, diamond flushes, spade flushes, and club flushes. So we add those up because they're non-overlapping. And then what do we do next? Well, we simply divide 5,148 by the total number of sample points in our sample space, the cardinality of the entire big ol' sample space, which was 2,598,960. So it's 5,148 possible flushes, all equally likely, out of 2.5 or almost 2.6 million, so around 0.2%. Okay. So if you're following all this, good. We've got a good foundation, and we'll do a couple more interesting problems.